Hey y'all, welcome back to Alakazam Math Made Easy. In the last video, we introduced the concept of limits kind of graphically and numerically and kind of went into some of the little nuances, especially as it relates to continuity. A little bit as a reminder, limits are very closely related to continuity, but that's just one of the helpful properties that they have. Another one, I guess a collection of them we'll go into more in this video, are referred to as the limit laws. And all functions have laws that are similar to this. They're not identical because, again, all functions are generally different. But for example, logarithmic laws or laws of logs um, follow some kind of similar trend. So what I'll do is I'll introduce each of the laws, give you the general form, and then I'll kind of derive it a little bit so you can hopefully see exactly where this all comes from. So to do this, what we're going to have to do is we're going to define some, we're going to lay out some definitions so that we're writing out the laws and understanding what they mean, right? So the way that limit laws will work is we're going to relate two separate limits, right? So we have the limit as x approaches a from one function, which will be called f of x, and then we'll compare it to or relate it with in some way the limit as x approaches a of another function. And we'll just assign these arbitrary values. So the first one we'll call m, and the second one we'll call n. And so what we're going to end up doing is we're going to end up, well, before we jump into that, I guess it's super important to note the similarities and differences between these two things. So what we're not doing is we're not comparing the limit as a approach or x approaches a, sorry. We're not comparing as x approaches a of f of x and limit as x approaches b to f of x. That's not what we're doing here. What we're doing is we're comparing two functions as the limit approaches the same value, right? So the first law, we'll call it, is the law of sums, which basically says if I take the limit of both of the functions added together, that's what this is, we're adding those two functions together, it's the same thing as summing the individual limits together. So basically what this is saying is if I take the two functions that I've defined here, right? So I've defined the limit of x plus 4, limit as x approaches 1 of x plus 4. And I've also taken the limit, the limit as x approaches 1 of 3x squared plus 1. And I've summed them together, but in this first line, what I've done is I've summed them, then taken the limit of the sum. And in the second line, what I'm going to do is I'm going to take the limit of each individually and sum them together. And I'll show you hopefully by the end of this that these are the same process essentially. So as a reminder, we talked about this at the end of the last video. If the function inside of the limit brackets, so for example, the functions inside here, if they're both continuous, we can evaluate the limit by just plugging in the number that we're approaching, right? So because x plus 4 and 3x squared plus 1 are both continuous functions, we can evaluate them by just plugging in 1, right? So this first one, limit as x approaches 1 of x plus 4 is 1 plus 4, which is 5. And the second one is the limit as x approaches 1 of 3x squared plus 1. That's going to be the same. Oh, just kidding. It's minus 1. That was almost my bad. 3x squared minus 1. Sorry. So if we plug in 1, we get 3 times 1, which is 3 minus 1 is 2. So we get 3 minus 1 is 2. And you'll see that either way I chose to solve this, I get 7. So that's what this first law is trying to tell us. The second law is very similar, right? So if the sums can work like this, you would imagine that the differences can work as well, but let's test it. So the limit as x approaches 1 of x plus 4 minus the limit as x approaches 1 of 3x squared minus 1. And then we're going to evaluate those just the way we did up above, where we do it independently. We're not going to go ahead and worry about whether they're continuous again because I used the same ones from before. So what we're going to do is it'll be 5 minus 2, because again, this limit evaluated equals 5, and this one evaluated equals 2, and that results in the limit of 3. So again, these match, which is just a basic proof that that's true. Moving on to the next one is essentially what happens if I were to multiply a constant through the function that I'm taking the limit of, right? So here I multiplied the function that we call g of x, that second function, by 2. And what we'll do is we'll end up seeing that if I do 2 times the limit as x approaches 1 of 3x squared plus 1, I should get the same thing, right? So that would be 2 times, if I plug in 1 into here, I get 3 times 1 squared, which is 3, plus 1 is 4. So I get 8 for that one. And again, as expected, they match. So let's try the law of products. So what that basically says is if I multiply 2 functions together, I should be able to multiply the limits of the individual functions together and get the same value. So the limit as x approaches 1 of x plus 4 multiplied into the limit as x approaches 1 of 3x squared plus 1, we get, let's see, this first one, we plug in 1, we get 1 plus 4 is 5. And we multiply it by plugging in 1 to the second term, which gives us 3 times 1 squared is 1, plus 1 is 4. And we get 20. So again, as expected, these match. Moving into the fifth law, the law of quotients, basically just like addition and subtraction were related to one another, we can expect that multiplication and division will be related to each other. So if I do the limit as x approaches 1 of 3x squared plus 1, and I divide it by the limit as x approaches 1 of x plus 4, I should get the same thing as if I took the limit of that quotient itself. So what I'm going to do is I'm going to test that theory, and I'm going to say if I plug in 1 to here, I'll get 3 times 1 squared plus 1 is 4. And if I plug in 1 to here, I get 1 plus 4 is 5. And simplifying that fraction, I get 0.8. And again, they match, thank God. The last two, again, are another coupled essentially relationship, where if I say I'm going to raise one limit to the power of any number, any n, it's the same thing as, I'm sorry, if I were to take the limit of any function raised to the power of n, it would be the same thing as taking the limit of that function and raising the limit itself to the power of n. So what I should be able to do is I should be able to say the limit as x approaches 1 of, so I actually already did it the way I was planning on doing it up here, so we'll try it differently. We'll FOIL this. So if you remember, FOILing is expanding any squared function, right? So I have x squared plus 8x plus 16. So that would be me squaring the function itself and then taking the limit of it. So again, this is a continuous function. It's not going to be undefined anywhere. So I'm just going to go ahead and plug 1 straight into it. So I get 1 squared plus 8 plus 16 is 25. which is the same function as here. Logically, as everything else has been paired, this last relationship will be paired. So limit as x approaches 1. Actually, we'll do a different example than that one because that one's kind of tough. We'll just do the inverse of this. So if I did x squared plus 8x plus 16, right? And I evaluate the limit of that, I'll start by this first step, taking the square root of that function, right? So the square root of that function is x plus 4. So now I can take the limit at x is 4, and it's continuous, so I can plug in 1. 1 plus 4 is 5. Now if I were to do it the other way, where I have the limit as x approaches 1, square root of that, x squared plus 8x plus 16. What I should be able to do is, instead of doing it that way, I should be able to say, all right, let me do it this way, right? I take the limit of that function and then square root it, right? So let's try that. So the limit as x approaches 1 of that function is, this is continuous, so we can plug 1 straight in. So we have 1 plus 8 plus 16 equals 25. So I basically have the square root of 25, which is 5. And that matches. So a lot of times what I hear people say is a lot of this is logical, right? A lot of this is something that even if you didn't 100% study intentionally and understand, you might accidentally do it just because it seems like something you're allowed to do. So that's good. Is what's good is that it's not super conceptually strenuous. But what you'll find is that down the road, these concepts will be absolutely critical for understanding the relationships between multiple limits. So it's important to lay them out, really familiarize yourself with them, work on, practicing the relationships between them. If you have a homework problem where it's not necessarily talking about this specifically, but it's something that you could do, I recommend trying to do it both ways just so you're comfortable with it. But these will absolutely be incredible tools down the line. So if you learned something from this video, feel free to like it. If you have questions still, leave them in the comments. I'll answer them as soon as I can. If you'd like to stay up to date on the stuff that I post, subscribe and hit the bell button to get notifications when I upload a new video. And as always, good luck.